On the top of this notes, you'll see that I have both the formulas that we learned last class for arithmetic sequences and geometric sequences exactly alongside the equation for linear functions and exponential functions. What do you notice about these formulas?
You have an exponent.
Yeah, these ones have an exponent. Okay, cool. What else do we notice?
They seem shorter.
The arithmetic has like a, no, I don't even know.
The x's and y's in the formulas for the functions. Yeah, okay. Maybe can we notice that this one in particular is like number, parentheses, plus a number, and number, parentheses, plus a number? So they're like clearly very, very similar to each other. And in fact, what I want us to learn today is that the common difference that we were working with last class acts exactly like the m in a linear function. And what does the m represent in a linear function? The slope. So your common difference is really the slope of the linear function that might represent that sequence. So if we look at all of the information across the top of the next box, for linear functions, right, we're looking at the linear functions, we know that their shape is just a straight line. Some sort of inclined line, maybe with a positive slope or a negative slope or a constant slope or a constant line. But either way, what we know about these is that over equal length input value intervals, the output values change at a constant rate. That constant rate, called the slope, is based on a change in addition, which is exactly why it acts like a common difference, because that's the sequence that changed with addition or subtraction, which is adding negative numbers. But I want to go further, and we started to make this connection during our classwork last class when I made you go back and try this with a calculator, is that when you run a regression, either for a sequence or for a linear function, you can use either option 4 or option 8 on the calculator to represent those linear functions. And once it's in our calculator and we put a y1 in there, we can do a whole lot of predicting the future, which is what we're going to work on today. I also want to make a connection when it comes to geometric and exponential functions. Do you notice that the common ratio, which is here in the center, is in the same spot as the b that represents the base of an exponential function? In fact, for geometric sequences that have a common ratio and exponential functions that have a base, those act the same. For exponential functions, which look typically like this, where they curve up in this concave up scenario, yes, over equal length input value intervals, the output values change proportionally, which means that the change or base in the formula is based on multiplication in the same way that our geometric sequences changed based on multiplication or division, which is multiplication of a fraction. Most of you guys figured this out when we went to the stat calc options last class during the flags game, during the classwork, that if we used option 0, that's for an exponential regression. So that's going to come in handy today. My goal for us today is to know how to clearly communicate whether a table of values, which could be a sequence of values or a function table of values, represents either a linear or exponential function. And we're supposed to be able to communicate that clearly in an example, not just like with numbers, but with words. Then we're also going to make a connection back to our calculator later on in the notes. So it says example 1. Selected values of several functions are given in the table below. For each of the table, determine if the function could be linear, exponential, or neither, and give a reason. So let's look at this first table. We always want to look first at the input values to see how the input values are changing. So in our table, we're going to annotate the table, and we're going to say how this is all changing. How are we changing from 0 to 3 to 6 to 9 to 12? Plus 3. So we have equal length input value intervals. They're changing at an equal interval. Sometimes, or a lot of times it's like plus 1, plus 1, plus 1, but for us still, it's an equal length input value interval. How are the outputs changing?
Minus.
Is that consistent the whole time?
No.
Are you sure?
Sorry.
It is consistent the whole time. So if your output values change with a constant change, that means that the function could be linear because we are using addition to change from question to question to question to question. So answering the question with linear is very important, but I also want the reason to be very clear. So we are going to say the function could be linear because over equal length input value intervals, which are changing by +3, the output values of f of x change at a constant rate. And we're going to say that that constant change was -2. So a couple things to notice here. We need to speak on what the input values are doing and what the output values are doing to clearly communicate that we know why this table represents linear functions. We are talking about the input values changing by +3 and the output values changing by -2 constantly the whole time. That would give me enough information to say that these are linear. If you're like, Ms. Quigley, where did you get this sentence from? It's exactly the definition here in the table. Over equal length input value intervals, the output values change at a constant rate. I'm just telling you the numbers in my explanation as well. Before I take your questions, let's see another one. If we look at the table for h of x, let's talk about the inputs. What are happening to all of the inputs? +2. Oh, so they're equal lengths. We're going to have equal length input value intervals. If we have equal lengths between our input values, we can just look at the change in the outputs. How are these outputs changing? They're multiplying by 2. We can see that 1 to 2 is times 2, and then times 2, and then times 2, and then times 2. So if we are changing with multiplication, what kind of function could it be? Ooh, if we're changing with multiplication, it could be exponential, because exponential is the one that changes with multiplication. This could be exponential. And the reason that we give is we say, because over equal length input value intervals, which we saw was +2, that's our input changes, the output values of h of x change, and then do not laugh at how many times I'm going to misspell this word. This word is my kryptonite. They change proportionately. Did I spell that right? Well, you get the gist. This is my kryptonite. This and the word necessarily, I can never spell them correct.
You ain't gonna judge us if we spell it wrong?
You got to get it close enough so I'm not confused that it's something else.
That's fine. I'll put
Now, how are we proportionately changing? What is our common ratio here? Times 2. So we're going to say times 2. So again, in your explanations. So here's the thing. Proportionately and proportionally are spelled differently, and I mix and match them. I think that's my biggest problem. Are you looking it up on how to spell it? Google's not helping you hard enough? Proportionately is how I spelled it. Is that right? How bad was I? Proportionally has 2 L's. Proportionately. You know what? We're just going to do our best. It is up here, but I was trying to do my best not to have to look at it because I know I'm trying to learn how to spell this word better. I don't know why. It's just the word that's going to be my kryptonite. Proportionately, you might have Googled proportionally. Those mean the same thing and can be used interchangeably.
Prop words ion additive.
Whatever it takes, everybody. Whatever it takes. Oh, my Lord. Okay. Let's do one more. Maybe I can spell all the words right this time. For the third table, let's first check our input values. How are the input values changing? +1, +1, +1, +1, +1. Okay, so we have equal length input values. We needed to make sure that they're changing the same way. Now we can look at the outputs. How are the outputs changing?
They're would it be
I mean,
either?
it's multiplying by your fraction.
Is it?
You can't multiply
You
anything
can't
by
add that, you
zero.
can't subtract that.
You're right. I can't add it. I can't subtract it. I can't even really multiply it.
You wouldn't divide it with
So is it going to be linear or exponential? It's going to be neither, but we know more than this. So watch this. This is plus 1. This is plus 3. This is plus 5.
This one's plus 7.
This is plus 7, which means this is...
Plus 2.
What kind of function did we learn about maybe previously in this course that has a second difference that's the same? Quadratic. So technically, to answer this question, because it didn't offer that, we would say neither, but we're smart enough to know that this is actually quadratic. And if I'm going to be sturdy enough to ask you about quadratics later, which I will, the function could be quadratic because over these equal length input value intervals, which went up by plus 1, the output values of g of x have a rate of change that changes at a constant rate. And yes, it sounds like I just used all of the same words over and over again, but I did. We are saying the output values have a rate of change that changes at a constant rate. That's saying our second differences are the same.
Do we have to remember to write this?
Yes.
That's annoying.
Nice.
No, or that's not.
The output values have a rate of change that changes at a constant rate. And here's how we remember that. The first things that we're finding right here is the rate of change if we're doing positives and negatives. This is the change in the rate of change. That's what you're finding.
It's still annoying to write.
It's still annoying to write. Okay. Let's look at this last one for the k of x function. We check the input values. How are the input values changing?
Plus 5.
Nice. We can always see that very easily that we have input values that are of equal length. What's happening with the output values? But I don't want to say divide by 2.
Multiplying by a half.
Thank you so much for remembering. This is multiplying by a half. So if we are multiplying by a number on my outputs, and it's the same every time, what kind of function could this be? Exponential. If I had asked you what kind of sequence could this be, what would you say? Geometric, very good. Now, this function could be exponential because over the equal length input value intervals we found of plus 5, the output values of k of x, good luck to me, change proportionately. I don't know why I stress so much about that word because I'm spelling it right.
You know how to spell nationality?
N-A nationality. Oof. Can I write it down? I don't spell good out loud. I spell better writing it down. Nationalal.
Where are you writing?
I'm writing it with my Apple Pencil on nothing. So I just need to write it with my hand. National. Ality.
We can't tell you yet. Just write it.
Write it on here? I'm gonna be embarrassed if this is wrong.
Proportionately national. I wanted to just kind of change the last part of this name.
You wrote it right. Hey.
Yeah.
Right.
Yeah.
So you're trying to tell me there's no E in proportionately? You totally could be right. Like I said, this word is my kryptonite. Anyways, okay. Are there questions besides just commentary on writing all of these sentences out? Are there any questions about looking at a table and deciding what kind of function it is?
Not really.
Okay. Do you all have your calculators?
Yes.
Oh, go get it real fast if you don't have it. Because in example 2, we need our calculator to be able to zoom past a lot of the hard work that I made you do last class. Remember how last class I made you plug stuff into an equation and like solve for the common difference or common ratio and then plug it back in and then plug it in again?
Yep.
Good thing we have calculators because we can do that a lot faster if we learn the following tricks. Example 2, a wild rumor is spreading that your wonderful APPC teacher won 3rd place in the world's coolest teacher contest. Check me out.
Miss Wilson?
There's you.
Next class.
What?
The number of people that have heard the rumor can be modeled using a geometric sequence. Let's highlight for a second the fact that it says geometric sequence, because we're going to politely ignore that it says geometric sequence, and we're going to treat this like the function that goes with geometric sequences. 43 people had heard the rumor on day 3, and 140 people have heard the rumor on day 6. According to the model, how many people to the nearest whole number have heard the rumor by day 10? Here's what I know. I know that on day 3, there were 43 people that had heard this rumor, this amazing rumor about your wonderful APPC teacher. And on day 6, there were 140 people who had heard this wonderful rumor. If we have 2 coordinate points, we have enough information to use a regression in our calculator to find not only the sequence formula, thus the exponential function, we can also predict the future. So I want you to go type in just these 2 points into your stat edit. I want you to use the option 0 of exponential regression. And then I want you to use that equation
How do I do that? Like, I have no clue.
to predict the future for 10. So, of course, we get our number out of our calculator here after running the regression. And our prediction for the number of people who have heard the rumor by day 10, our calculator is telling me 675, wait, I should say it right, 5.5759. But of course, remember, we are looking at a sequence of numbers. Sequences, specifically ones that are talking about people. Should we be answering with decimals when we're talking about people? Nah, let's round to a whole number. It even says 2, but like that makes sense too. So this would be 676 people. 6, 7, 6. Y'all started it.
There's some online dude.
So let's try this again, okay? In the next question, it says, a large theater has rows of seats where the number of seats in each row can be modeled by an arithmetic sequence. We read arithmetic sequence, but we think linear function because they're related to each other. If the 5th row has 31 seats and the 11th row has 49 seats, how many seats are there in the 25th row? What are the 2 coordinate points I get from that information? 5, 31 and 11, 49. This time, since it's an arithmetic sequence, I can use either option 4 or option 8 when I go to the linear regression screen. Let's use 4 this time. Linear regression. Then you're going to go ask the calculator to do y1 of 25 because you're asking it to predict the future. So once we throw that into our calculator, we should get out. Again, it's a sequence of numbers, so we're just using the fact that it's related to a linear function to be able to solve this question. 91 seats.